Watch your speed. No, now you're drifting.
How am I supposed to know my position and my velocity at the same time? Don't you know the laws of physics? It turns out that physics is a little more complicated than that. Heisenberg's quantum uncertainty principle states that the more precisely you know an object's position, the less precisely you can know its momentum, and vice versa. That seems a little counterintuitive, but we're used to observing objects like baseballs and vehicles. To understand the quantum uncertainty principle, we need to look at things just a little bit smaller, like atoms. When you think of atoms, you might picture a giant nucleus with little electrons orbiting around it, like planets in our solar system. In classical physics, this seems pretty reasonable. However, quantum physics shows that our universe is stranger than this. Particles don't have predetermined positions and momentums like we would expect. Instead, when we measure these quantities, the result is random, described by the quantum wave function. The wave function is a sort of probability wave, defining which positions, momentums, or angular velocities we are more or less likely to observe. Now, most shockingly, this wave doesn't encapsulate our ignorance about reality. It is reality. This function of probability provides the most complete description possible of what it means to be a particle. Let's take a break and talk about measuring with my photon gun. I can shoot a wave of light at my car, time how long it takes to bounce off and get back to me, and since we know the speed of light, we can calculate how far away it is. Quick burst-like waves give me better measurements of position, since the shorter the wave, the less time the car has to move while the wave is hitting it. I can measure the car's velocity with a wave by measuring how much it is compressed or spread out on the way back, something called the Doppler effect. Here we want to use a longer wave, since the more time we take to observe a frequency, the more confident we can be about its value. Shorter waves give us better measurements of position, while longer waves give us better measurements of momentum. We can't have the best of both worlds. Since matter is fundamentally described by the wave function, we can understand quantum uncertainty with this same basic idea. When we measure a particle's position or momentum more and more closely, the wave function for the other quantity spreads out. No matter what, we are certain to have uncertainty. Heisenberg proved that a wave-like description of matter makes this effect inevitable. If all this quantum stuff is unsettling, that's okay. For all of human history, we have understood our universe at deeper and deeper levels, overcoming our initial reluctance to do so. We don't know what lies beyond quantum mechanics, and that's why it's important to ask questions, to be skeptical, and to approach the world with a desire to explore. You never know what you might find.